Everybody, welcome to our second session. This is going to be on debugging and programmability of SDNs. I personally think this is some of the coolest and most interesting stuff in software-defined networking. So our first talk today is going to be by Andrew Ferguson. He's a third-year student at Brown, working in distributed systems under Rodrigo Fonseca. And with that, Andrew.
Good morning. My name is Andrew Ferguson, and I'm going to introduce our implementation of hierarchical policies for software-defined networks. This project is joint work with my colleagues at Brown University, Arjun Guha, Chen Liang, Rodrigo Fonseca, and Sriram Krishnamurthy. We're working on a project we call participatory networking, which integrates end users and their applications directly into the management of the network. We are motivated by the multitude of scenarios in which network intentions are trapped inside the end host. For example, I like to watch movies at home with Netflix. And while there are many reasons why Netflix may begin to buffer, one reason is because a second laptop has begun a network backup. And while there are many proposals for how to solve this problem, it still exists. With participatory networking, the Netflix application can inform my home network of its bandwidth and latency requirements and be guaranteed a level of service. Turning now to an enterprise network, we see shared links supporting many hosts. And if one host suffers from a denial of service attack, we may need more than a local firewall rule to protect the network. Today, we can call the network administrator, or with participatory networking, the victim host can install a network firewall rule on its own. Furthermore, in proposed data centers, connectivity is by both commodity Ethernet using copper cables, as well as software-controlled optical networks connecting the top-of-rack switches. Today, these circuits are reactively established by heuristics, whereas with participatory networking, any application with large traffic flows, such as a MapReduce or disaster recovery, can notify the network controller and pre-configure a circuit configuration. If we follow the analogy that software-defined networks are developing an operating system for the network, participatory networking is building the end-user system call, an API for SDN. Like previous work on operating systems, SDNs began by providing abstractions over the hardware. We believe it's time for SDNs to similarly evolve into arbiters that support multiple principals sharing and controlling those resources. One challenge, of course, is the development and implementation of a semantic, which delegates authority from the network administrators to the people, without sacrificing high-level requirements such as safety, security, and fairness, and low-level properties such as freedom from routing loops and traffic black holes. At this year's Hot Ice workshop, we introduced the semantics for delegation and a protocol for requests. Today, I'm going to focus on the design of this language and its efficient implementation. We call this prototype and controller Pain. The core of Pain's design is a policy language we call hierarchical flow tables, or HFTs. Hierarchies are a natural way to express delegation. In Pain, we have two hierarchies. The first is a static hierarchy of the privileges granted to users and their applications. This hierarchy sets the stage for a dynamic hierarchy of policy requests. As users and applications make requests, this policy tree grows, always within the bounds set by the privileges hierarchy. Frenetics proposed an abstract model in which every packet is processed against global policy by the central controller. We use this same model and view packet processing as a result of evaluating each packet against this global policy tree. First, we identify the matching policy node, shown here in green. Next, policy nodes emit their actions. When multiple subtrees have produced actions, we apply user-defined operators at each node in the tree to combine the actions. Here, the sibling operator was applied. Next, we combine the children's action with the parent using a parent operator. Note that in this case, the parent did not produce any action, which we denote by 0, our special don't care action. This process continues until a final action is emitted from the root of the tree. I want to talk some more about these combination operators. We've seen two of the operators already, the plus S operator, which combines sibling actions, and the plus P operator, which combines the actions of a parent and a child. We also have a plus D operator, which combines multiple actions inside of a single node. The requirements on these operators are very basic. First, they must be associative, and second, they must support the 0, the don't care action, as their identity value. With these minimal requirements, we can convert the HFT into a realizable implementation using a strategy I will describe next. But first, let's look at how we define these operators in Pain. Pain currently defines two actions, access control and guaranteed minimum bandwidth, or GMB. Pain's plus D and plus S operators are the same and implement a basic policy in which deny requests override allow requests and always take the maximum of 2 bandwidth guarantees. With the plus D operator, Pain allows child nodes to override parent nodes. The HFT itself is agnostic to the specific policies of these operators as long as they satisfy the identity and associativity requirements. For example, we could develop operators that resolve conflicts according to specified priorities. So, how do we implement these hierarchical flow tables? Now, in an ideal world, we could simply pass the HFT to the switches. And when packets arrive, the switches would evaluate the tree just as we did on the previous slide. However, today's switches aren't capable of performing this evaluation, and therefore, rather than send every packet to the controller, we developed a compiler which linearizes an HFT instance into 2 traditional flat open flow tables that are collectively equivalent to the logical policy tree. Our open flow controller then installs these tables on the switches, allowing the network to implement the HFT's decisions with hardware support. Our compiler works in 2 stages. First, the compiler linearizes the HFT into a single table we call the network flow table. If the network were connected by a single big switch, we might install this network flow table directly onto that single switch. In the compiler's second stage, it translates the network flow table into individual flow tables for the distributed open flow switches. And during this stage, the compiler relies on network information base, or NIB. The design of our NIB is inspired by Onyx, and it describes the state of the network, including host locations, link statuses, queue availability, switch configurations, and more details. For example, the compiler uses the NIB to implement a bandwidth reservation by finding a circuit with the required bandwidth, sending commands to create the necessary queues, and finally updating the open flow tables with the required forwarding decisions. The NIB also allows Pain's compiler to choose where in the network to implement desired policies. As a simple example, it places rules which drop traffic as close as possible to the traffic ingress port. In this experiment, we have 2 wireless clients communicating, and one suffers from an attack, and the transfer rate drops. With a local firewall rule, the transfer only slightly recovers. Using Pain to install the rule, the transfer fully recovers. And as the source of the traffic moves, the rule can shift with it. Updating the NIB is the responsibility of our OpenFlow controller, and any updates are propagated back into our compiler service. The compiler may then construct a new set of OpenFlow tables, which continue to implement the decisions of the network flow table in this new environment. Seen in this way, you can think of the network flow table as a set of invariants which we would like to maintain, and our compiler's second stage as a service which maintains those invariants. Now, as we saw on the last slide, this is a complex and concurrent system, and complex systems have bugs, even if you write them in Haskell, as we did. And I'd like to briefly tell you how we proved a key portion of this system correct. So as a starting point, we know what it means for a hierarchical flow table to process a packet. The packet enters the switch, the policy tree nodes produce their action, and a result action is yielded after applying the combination operator. To make this efficient, we built a compiler from declarative hierarchical policies to a linear flow table. But how do we know this compiler is actually correct? Compilers are also notoriously difficult to get right. If this compiler has a bug, it's not that a program may crash, but the entire network may go down, or a more subtle error may occur, such as traffic that should be blocked may instead be submitted. So, using the cost proof assistant, we modeled and wrote a proof of the translation from HFT to OpenFlow tables. Cost lets us write programs in a functional language similar to ML or Haskell, and gives us the ability to prove properties of these programs. So let's look at what we actually proved. Logically, the HFT processes a packet and produces an action. When we compile the HFT to a network flow table, the flow table produces exactly the same action on the same packet. Proving this theorem requires a formal semantics for hierarchical flow tables, which you can find in detail in our paper. The paper also contains the precise statement of the theorem, and the mechanized talk proofs are available on our website. So, we've developed a prototype participatory network which carries traffic in our lab, and we use it for our day-to-day development and internet connectivity. This network supports wireless clients using OpenFlow for OpenWRT work, and wired clients using OpenVSwitch. For this, we have a working OpenFlow controller which implements HFTs, including guaranteed bandwidth and access control. We are currently developing a set of client libraries to assist application development using our protocol, and have ported a few applications to use our testbed, including Zookeeper. Our paper provides a first evaluation of a participatory network's ability to protect Zookeeper's low latency traffic from bulk data center flows. And of course, no talk would be complete without mentioning that more libraries and more ports are on the way, so please stay tuned. We are also developing more operators and scenarios and planning to evaluate the scalability and performance. And you can learn more about our prototype controller on our website and by downloading the source on GitHub. We've also built a demo virtual machine using Mininet, and we're planning to migrate this to Mininet Hi-Fi to provide some better demos. So please get in touch with us if you're interested in checking this out. And with that, I'm happy to take your questions at this time, or you can direct them to my collaborators in the audience. Thank you very much.
So we have a couple minutes per question. Anyone? If not, I actually have a question. No one? All right. So the question is, the compiler is actually fairly nice in terms of you can take something that people can ration about and break it down to something hard for people to ration about, but what is the expected state explosion from the result of that?
No.
Right, so how many rules in the hierarchy results in how many rules in the flow table? Do you have an approximation to that?
So I can't give you an exact number, but we definitely follow the problem of, we exhibit the problem of the cross-product rule explosion that happens, and we're hopeful that table support in OpenFlow 1.1 and later will help us solve that problem. But yeah, we definitely see that, and we do some optimizations in order to try to keep that down. Like for example, if one rule we know is shadowed by a rule with higher priority, we don't put that in the table. We combine rules that cover the same space in order to keep them down to a minimal number of rules. I mean, we try, but you can't get around the cross-product explosion. So, yes?
Okay, you listen often. I wonder if you could expand a bit on how clients and how current applications can use it.
Yeah, totally. So our client application either knows about the pane controller already on the network, or could receive it from DHCP or something, and then it follows a protocol that allows it to ask about sort of what kind of access it has, it identifies itself, it can submit requests and ask for different resources, and if those requests can be granted, it sends it back. So our previous paper covered that in more detail, so I didn't want to dive into it in this discussion, but yeah, check it out. Thank you.
All right. Any other questions? And we'll thank our speaker. Thank you. while he's setting up, our next speaker is Andy Bolney, soon to be graduating student from Yale, working with Paul Hoddick.